Hey, everyone. Today I'm going to share with you the new technique called the EC surface plasma resonance, and so some of the basic principles and applications. And just as a brief review at the beginning, so I will go through the operation of surface plasma resonance first, and then a brief review of EC, and finally combine the two, and followed by some application examples. So surface plasma resonance. The surface plasma are the electromagnetic wave resonances trapped at the interface between the metal conductor and the insulator. And when you shine a laser to the interface at a certain angle, so all the light will be reflected. And when you change the angle at some angles, then the instant laser will start to resonate with the surface plasma. And in that case, all the instant light, the energy will be absorbed by the surface plasma, and therefore the reflected light will become very low or become zero. So when you detect the reflected intensity, and you will see a dark band or a minimum on the detector. And this special reflection angle, which is called the SPR angle or SPR response. And this angle is extremely sensitive to the surface condition, and particularly sensitive to the dielectric properties of the interface, and which can be affected by many different processes such as absorption, disruption, and chemical reactions, and surface electronic states, and density, thickness of the film, etc. So one of the applications is to use this technique to measure the binding of chemical reactions, the binding constants of between molecules. So in that case, we have the surface plasma resonance to set it up, and then you have one molecule stick or fixed onto the surface, we call the ligand. And then when you start to putting the another molecule, and when this molecule binds to the ligand onto the surface, at the surface, and it will cause the shift in the SPR angle or the SPR response. And depending on the stage and the during the of the reaction, and you will see the SPR angle shift constantly. And you can record this SPR response, SPR angle, as a function of time for the whole process of this binding reaction. And then you will obtain the spectrum, the so-called SPR sensogram. So which basically record the whole process for the association and the dissociation of the reaction. And by analyzing this association and the dissociation, you can get those kinetic parameters such as K-on for the association, which is the rate constant for the association, and K-off for the dissociation, and of course the affinity, which is equivalent to the equilibrium constant of the reaction. So this is for the how the SPR, and for electrochemistry, it's actually quite different technique. So electrochemistry is very powerful in controlling the process at a solid-liquid interface. So you basically have a solid electrode, a metal electrode. And by controlling the potential or controlling the current flowing to the electrode, you can actually control the reactions happening at the electrode surface, therefore control the stage or the physical stage of the interface. And with this technique, you can study things like the charge transfer for the redox reactions, and for electrodeposition, and for corrosion, and many So it's a very powerful technique. So when you combine the electrochemistry and the SPR and put them together, now you have the electrochemistry, which you can control the process happening at the surface, and SPR can actually determine or measure the physical conditions of the interface. Therefore, you have complementary observations by combining the two and also added control parameters. And with this, you have a further degree of freedom to design new applications. So you can see the for the electrochemistry, you measure the CV, the cyclic voltammetry of the process, which shows like the peak here shows the electron transfer, the reduction and oxidation of the materials at the surface, and the SPR recorded the physical condition of the physical property of the interface related to its dielectric constant change, either due to the oxidation state or changes in the film thickness and those parameters. So we'll get more details on that later on. So as we see, the surface plasma resonance actually the SPR response changes as a function of voltage here. So essentially, there's two major contributions to this change. So, which is the first of all is the refractive index, or the dielectric property, and second is the film thickness, and the other one is the charge density or the electronic state of the interface. And those three are kind of intercorrelated, and by designing the right condition, so you can single it out any individual one. I mean, so you can see which one is the dominating factors, and by designing the right experiment, you can actually study one of the major contributions from of those three. So for the combined technique, you have three. You can actually usually this is four of the typical or the characteristic applications. So first of all is to look at the structure changes in thin films, and the second is to look at the conformation changes of proteins due to the redox reaction occurring to it. And the other thing is that you can use this technique to develop new sensors for measurement or detection of biomolecules. And the last one is a very interesting application, which actually have a special designed technique to study the intermediates of reactions. So I will show you that. So now let's look at the first one. So this example is shows the conformation changes of a protein, so cytochrome C. And this one has this Hemi group, which can be reduced or oxidized by controlling the potential. First of all, it forms when it's attached to the surface, it will have a typical SPR angle. And then by using the electrochemistry to whether to oxidize or to reduce the Hemi group, so controlling the redox state of the Hemi group. And what you get is this molecule either open it up or close in, so it changes its conformation. And this conformation will change the physical state of the interface, and correspondingly it will be measured by the SPR. And so the cyclic voltammetry on this left figure here, so you can compare the one is that has a pure buffer. So you see the CV shows only a square-like typical capacitors behavior, which shows corresponding to the double layer capacitance of the system. And the other one, when you have a cytochrome C, and you have the oxidation peak and the reduction peak corresponds to the reaction of the Hemi group, and so indicates the electron transfer during this process. And this oxidation and the reduction cause the physical state change, and is measured by the SPR. So again, here in the SPR signal as a function of potential, you see for pure buffer, you see a kind of like a flat line. There's a very minimum changes corresponding to the potential sweep. And for the cytochrome C, the changes of the SPR signals very reproducible, repeatable, corresponding to the oxidation stage of the heme group. And this is another kind of typical, very unique applications for the EC-SPR. So what we're looking at here is self-assembled monolayers on the electrode surface. And the molecule used here is ferrocene terminated alkene cell. And the cell group is actually attached to the gold with the ferrocene and pointing to the solution. The ferrocene group can be oxidized or reduced by controlling the EC. So which shows that by the CV, you have a very symmetric redox reaction peak here. And then by oxidize or reducing the ferrocene, so you change the formation structure of the cell layer, so which is caused by a slightly tilting of the molecules, standing on the surface. So a very small change. The angle tilts from 2.1 degree to 2.7 degree, and such a small change was actually will give a change in the film thickness formed by 0.08 to 0.09 nanometers. And this is a very, very small change in the film thickness. However, because of the very high sensitivity of the SPR detection, you can actually determine and measure this changes caused by the oxidation stage of the ferrocene group by the charge transfer. The other application here, this is used for combining EC and SPR to find the optimize the process of developing the biosensor for glucose detection. And the film is polypyrrole and glucose oxide. And first of all, using the EC, by cycling it, you can actually control the film thickness. And second, by combining the EC and the SPR, you can find the optimized doping concentration of the ion concentration, which is the chloride ions in the film, which is a very important parameter that controls the sensitivity of the sensor. And the last image here shows is again by combining the two techniques, you can actually find the optimum operation potential for the detection. So here is actually some real testing results for using the sensor developed by using the method. And so first of all, here on the left side, it shows the glucose detection of 3 different concentrations and the linear dependence between the concentration and the SPR signal. And on the right is actually a comparison of this new technique, this new developed sensor and SPR sensor with some other experimental techniques reported in the literature. And first of all, the measurement between this new technique and the other techniques are very well agreed with each other. And secondly, the accuracy is pretty high, so you have a very small average deviation. And so this is actually one of the very widely used application right now for developing new sensors for biomolecule detection. And this is actually the last application I'm going to show you, but it's a very interesting one. So what we are looking at here is a system, the hydroquinone and the quinone redox pair. And between the redox reaction, there is some intermediate stage molecule produced during the process, which we name it big Q star. And this intermediate state, as an intermediate state, it just produced and then disappeared, come and disappeared, in the reaction. So it's difficult to measure the behavior or the properties of those two. For example, the lifetime of those intermediates. So this special designed technique is actually a combined EC with SPR, so we can actually measure the SPR at different stages of the time window. So, for example, we can produce the reaction, the intermediate at one state, one site, we call the, say, the position 0, and then you can measure at the different positions, like 0.1 second or 5 seconds after. So this time between those can be controlled by the flow rate of the SPR flow system. And the result is shown here. So first of all, at the potential 0, you generate the intermediate molecules, and by controlling the potential, and then you can measure the changes of the intermediate materials as a function of time. By analyzing this data, you can actually figure out, for example, the lifetime of this reticule, which in this case is roughly about 20 milliseconds. So this is actually one of the a powerful technique, a new application. Like I said, you can design based on these two techniques. So those are all the applications, and the applications, of course, may require the hardware. So these are the two different EC modules we provide for the EC SPR. The first one is a static model. So you basically have the reference electrode, counter electrode, and working electrode also has the sensor, and have the SPR measurement. And in this case, the electrolyte, the pump into the, it's dropped into the cell, and it stays there, and you study the reaction, so there will be, it's a static system. And then the second one, we call the EC dual flow module. So in this case, all the electrochemical configuration is still the same. You have the reference and counter, the working, and the SPR. So the new thing here, the unique thing here is you have a specially designed flow system for introducing the electrolyte dynamically. So in this case, you can have your electrolyte flow in constantly. So you can either introduce new molecules and new components to it, new compounds to the electrolyte, or just controlling the reaction process. So I think that's all I'm going to share with you, and hopefully that give you some basic understanding of what you can do and how this is done, and hopefully that will help you in your future research projects. Thank you very much.